Hello students, so in my previous lecture I gave you the three guidelines related to the importance of order of events in organic synthesis. So what were that three guidelines? First was that first of all we should look for the combination of substituents present in a target molecule. Second was that if it is difficult to add some substituent in a target molecule, then it is the better strategy to not to disconnect that substituent. And the third guideline that I told you, that we should check for the relationship between the substituent present in a target molecule, and then we should disconnect the target molecule in such a way that the reverse reaction gives the target molecule having the substituent with proper orientation. So these were the three guidelines. Now let's discuss the fourth guideline. So guideline number 4. So what this guideline number 4 tells? It tells that the most electron withdrawing group is to be disconnected first. Suppose if in a target molecule various substituents are present, then we should disconnect the most electron withdrawing group. So what we can write, if more than one group, or we can say substituent, is present in a target molecule, then most electron withdrawing group is disconnected first. Okay, so let's take one of the example to explain this one. Suppose if we have a target molecule in which various groups are present. So this is one of the target molecule, and if we see this target molecule, one of this two NO2 group are present. This is your methyl group, methoxy group, tertiary butyl group is present. So if you will see, then out of this all, the most electron withdrawing group, this NO2, is the most electron withdrawing group. So according to this guideline 4, this electron withdrawing group that should be disconnected first. If you will not disconnect this NO2 electron withdrawing group first, or if you are disconnecting, suppose methoxy group is, or suppose this tertiary butyl group is disconnected first, then if you will write the reverse reaction, then you will not get the same target molecule. So let's see it. Okay. So let's see that first of all I am writing its disconnection. Okay. So suppose what I told you, first of all we should disconnect this one, the most electron withdrawing group. First it should be disconnected. So if I disconnect it, then what we can write? Okay, and plus you can this nitronium ion, and that is the synthetic equivalent, that is HNO3 nitrotic mixture plus H2SO4. Okay, now if you will disconnect after this, so first of all I have disconnected the most electron withdrawing group as per the guideline. Now I will disconnect, I can disconnect suppose this one. Okay, now I am disconnecting this one. So what you will get, plus okay, so tertiary butyl chloride, these are the two synthetic equivalents. So here this you can write here this FGI, or here you may write Friedel-Crafts alkylation reaction via Friedel-Crafts alkylation reaction. If this is the molecule, then you can add this tertiary butyl group to it via Friedel-Crafts alkylation reaction if you go back. Now what we may do, so this group, if we want to add this one group, then this group is difficult to add. That's why we can do the FGI for it. Again, I will write the FGI, functional group interconversion, and this group can be interconverted into this OH. Means if we go in a backward direction, then OH can be converted into this methoxy group via the in presence of dimethyl sulfate and some base. Okay, now this molecule is the easily available molecule. Okay, this is the metacresol, which is easily available in lab. So as per the first guideline, as this is readily available molecule, that's why this should not be disconnected further. Okay, so now if you write the synthesis of this reaction, let's write the synthesis. If you write the synthesis, then we should go in a backward direction. So now this in presence of dimethyl sulfate and some base. So base will extract this OH, and this methoxy, this CH3 group will come. So you can, this methoxy group, that is interconverted into this methoxy group. Now we can do this Friedel-Crafts alkylation. So we have this tertiary butyl chloride, and this tertiary butyl chloride will add either at this para position or ortho position. So ortho, as this is the ortho directing, ortho and para directing, so this will insert this tertiary butyl group either at this position or this one position. And similarly, this is also a ortho para directing, so this will also insert the group either at this position or this position or this position. Okay, so the main product that we want to get, that can be isolated. So this can be isolated out. And now further we can do the nitration. Sorry, single arrow. I should write the single arrow. So in nitration, now as these groups are ortho and para directing group, so they will add, no, that's why this nitronium ion will add at this position. Either this position it can be added, or it will not be added at this position, because this is one of the sterically hindered group. So that's why now we may add the nitro group over here. Okay, so this is the correct pathway. So first we should break this electron withdrawing group. So electron withdrawing group is disconnected first. Now suppose if we don't disconnect this nitronium ion first, or this electron withdrawing group is not disconnected first, then what will happen? So let's see the result. So suppose I disconnect it suppose if we have this target molecule, and let's disconnect. First I am disconnecting first. This is disconnected first. Tertiary butyl is disconnected first. Then what I may write, so this CC bond is disconnected. Okay. Now I am disconnecting this nitro. Okay, now I will disconnect this one. Okay, so what I may write, here plus and further we can do the FGI to convert this one into this cresol. Now suppose if we write the backward reaction, if we write the synthesis of this, then what will happen? So as you can see, first of all, we can get this one methoxy group. In place of OH, we can get the methoxy with the in presence of this dimethyl sulfate. After this, if we do the nitration, of this, then what will happen? So you can see, if we have now, let's do the nitration of this. Then, as this is your ortho-para-directing, and this is also ortho-para-directing. Okay, this is ortho-para-directing, this is also ortho-para-directing. So that's why this nitro group may come here also. Okay, and as well here. So this may come here also. And further, if you want to do the Friedel-Crafts alkylation, if you don't want to do the Friedel-Crafts alkylation, then the target molecule, you will not get the same target molecule. So that's why this path is not correct. So this path is not correct. This is your correct path. It means always we should first disconnect the most electron withdrawing group from the target molecule. Okay, so this is the guideline number 4th. Now let's see the guideline number 5th. Okay, so let's see the guideline number 5th. So what this guideline says, that it says that if sometimes the FGI may be needed before disconnection, so that it may change the directing effect of the substituent. Okay, so before disconnection, sometimes we need the FGI. So that FGI, via FGI, we will change the directing effect of the substituent, and then we can get the correct target molecule in a reverse reaction. When we write the reverse reaction, then only we can get the correct target molecule. Okay, so let's write it. Sometimes FGI is needed before disconnection so that it may change the change the directing effect of the substituent. Okay, so let's explain it with the help of example, then it will be more clear to you. Okay, so suppose if I have one of the target molecule, so if this is the target molecule, okay, then in this case, if we want to get this target molecule, then for disconnection, first of all we should change the directing effect of this substituent. Okay, so here we need the FGI. Here we need the FGI, and I will change the directing effect of this substituent. So this substituent is meta directing, whereas this is also meta directing. Okay. But as you can see here, both the groups are para to each other, whereas both are meta directing. So this is not possible. So that's why this group should be interchanged into some other group. So if I interchange this into CH3, that can be changed into CH3 in presence of, CH3 can be changed into CCl3 in presence of Cl2 PCl5. Okay, so here I have changed the directing effect of this substituent. So this is meta directing, whereas you know that this methyl group is the ortho-para-directing. So this is ortho-para-directing. So I have changed the directing effect of the substituent so that I get the same target molecule. Now I can disconnect it. Now I will disconnect it from here. Now I can disconnect it from here. I can disconnect. Okay, so what I will get? Toluene plus this Cl2. Okay, so now if you will write the synthesis, now I will write the synthesis, then you will get the same target molecule. Craft. This is chlorination, and you will get here chlorine, because this is para-directing, ortho-para-directing. So you will get a chlorine group at a para position, and now we can change this into this one in presence of Cl2 PCl5. So I will change this into the target molecule. This can be changed to target molecule. Now if we will not do this one, then in that case what will happen? This group will be the meta to, both will be meta to each other. So here we need the FGI, so that we may change the directing effect of the substituent and we may get the target molecule easily. So some of the example where the meta-directing group is changed into the ortho-para-directing, and ortho-para-directing group can be changed into the meta-directing. So if I write, suppose this is ortho-para-directing group, for the CH3, if CH3 is there, then that can be changed into meta-directing via FGI. We can do the FGI and we can change into meta-directing group. Suppose it can be changed into the COOH group in presence of KMNO4. Similarly, in the CH3 can also be changed into via FGI. We can change, suppose I have written Cl2 PCl5, it can be changed to CCl3. Similarly, CH3 can also be changed into CHO via Eater's reagent, in presence of Eater's reagent, this can be changed, and in the same way, some of the ortho-para-directing group or some meta-directing group. We have some meta-directing group, and that can also be changed into the ortho-para-directing group. Suppose if we have NO2, if we have NO2, then this NO2 group that can be changed into NH2 group via this reduction. So this can be done. Reduction that can be changed. Okay, so these are some of the example where we can do FGI, and via FGI we can change the directing effect of the substituent. Okay, so let's see another guideline. So guideline number 6, what it tells that sometimes we can add the nucleophile to the benzene ring via diazotization reaction. So we know that this benzene ring is very much susceptible to the electrophile, and or we can say the electrophile can be easily added to the benzene ring because it is a electron rich one. But if we want to add the nucleophile to the benzene ring, then it can be added via diazotization reaction. So we may add nucleophile to the benzene ring via diazotization reaction. Okay, so let's take the example. For example, suppose I write this diazotization reaction. Suppose if I have aniline, then that can be converted into diazonium salt, and this diazonium salt can further be converted into here we may add the either we may add CN group, because this N2 being good leaving group, it will leave out, and we can substitute this one by the cyanide group. Similarly, we can substitute it by Cl group in presence of CuCl, copper 1 chloride, CuCN. In the same way, it can in presence of copper 1 bromide, we may add here bromine group also, or in presence of this H3PO2, we may convert it into we may substitute it by the hydrogen also. So these are some of the reactions. Now if we can add the nucleophile. So these are the CN minus, chlorine minus, Cl minus, Br minus. So these are the nucleophiles. So nucleophile can be added to the benzene ring via this diazotization reaction. Okay, so let's take one of the example. If I take one of the example, okay. Now suppose this is the target molecule. Suppose this is your target molecule, and now, so if we want to add any nucleophile to it, first of all, this COH, it cannot be easily added to it, so that's why this can be converted into the another functional group like CN. So cyanide can easily be added to the nitrile group, can easily be added over the benzene ring. But as this CN being the nucleophile, so this nucleophile cannot attack directly on the benzene ring. That's why this can be added via the diazotization reaction. So now what we can do, again we can do the FGI, or we can do the FGI, and we can convert this into this NH2 here. So this will takes place via diazotization reaction. Or Sandler's reaction. Okay, now we can do the FGI. That can be converted into NO2 group. So we know that this NO2 can easily be added. This nitrogen ion can easily be added. Okay, so now this can be disconnected. Now this can be disconnected, and we will get the biphenyl, which is readily available, plus HNO3 nitrogen mixture, H2SO4. Okay. So this is the guideline number 6. If we want to add a nucleophile to the benzene ring, then it can be added via diazotization. So for example, here if we want to add this nucleophile, CN as a nucleophile, then first of all it can be we should have the NH2 group, and that can be interconverted into the CN via diazotization reaction. So let's write the reverse reaction for this. So if I write the reverse reaction, so first of all I have biphenyl, this in presence of nitrogen mixture, it will give you so nitro group will be attached over here, not here, due to the overcrowding here. So now we can convert this into NH2 group by reduction. Further, we can convert into the diazonium salt, and further in presence of copper cyanide, copper 1 cyanide, it will give you this CN here. Okay. And this on hydrolysis so this will give you the target molecule. So this in the same way we can add other nucleophile also over the benzene ring. So this is the guideline number 6. Now let's come to the last guideline, that is guideline number 7. Now this guideline tells that if we want to add two ortho-para-directing groups matter to each other, then this can be done by the addition of a dummy amino group, and the dummy amino group can be removed by diazotization followed by reduction. Okay, so let me write it. If we want to add two ortho-para-directing groups matter to each other, then this can be done by the addition of a dummy amino group. Okay. And this dummy amino group can be removed by diazotization. Followed by reduction. So this is guideline number 7. So what this guideline number 7 tells, that if we want to add a orthopara directing group, two orthopara directing group on a benzene ring which are meta to each other, then this can only be done by the addition of a dummy amino group to the benzene ring. So let's take one of the example. Suppose we have a target molecule in which two orthopara directing groups are meta to each other. So if you will see, then these two are the orthopara directing groups and they are present meta to each other, which is otherwise not possible. Okay. So and one of this COH group is present in a target molecule. Then how can we obtain a target molecule in which two orthopara directing groups are present meta to each other? So this can only be done in presence of a dummy amino group, by the addition of a dummy amino group. This can be done by the addition of a dummy amino group. Okay. So if we how can we done it? By the addition of a dummy amino group. So first of all, what we can do, since this one of the NH2 group is present over here, then this NH2 being this can only be done by the reduction, this can only be added by the reduction of a NO2 group. That's why I am interconverting it into NO2 first. Okay. Now we can add a dummy amino group. So why we are adding only amino group? So why we are adding only dummy amino group? Why not other amino group? Because this amino group can easily be removed also. So we should add such a group that we can remove it also. Okay. So amino group can easily be removed. That's why we are adding a amino group as a dummy. So now we can add this amino group at this position. Why at this position? Because you can see this is this OH being orthopara directing, so here it can be added. COH being meta directing, that's why it is added over here. Okay. Now, and this will also direct this NO2 group at the ortho position. Okay. So now we can remove this one. This NO2 group can be removed. That is, CN bond is disconnected over here, and okay. Now this can again be interconverted into NO2 group. Via FGI, and this can further be disconnected to get salicylic acid as a starting material plus this HNO3 plus H2SO4 as a nitrogen mixture. Okay, so here this can should not be further disconnected according to the first guideline, which tells that we should we should look for the combination of substituent present in a target molecule. So this is one of the combination of substituent present in a target molecule, and this should not be disconnected further. Okay, so now we can write the synthesis. So while we write the synthesis, then we can see that this NH2 group should only be present at this position. Now, suppose we have now the starting material as a salicylic acid. So if we do the nitration of this salicylic acid, then the nitration will occur at this position, para to this OH and meta to this OH, and it can also be added over this position, that is ortho to this OH. So to avoid this problem, first I will do the protection of OH group so that the NO2 group don't add over here. So it should only be added over here, so that we can get the if we go back, then we should have this NO2 group at this position. So that's why I will first protect this OH group. So protection of OH group in presence of this acetylation will be done, so that for protection of OH group. And after that we can do the nitration. So I will get OH, COOH and this NO2 group over here. So this OH is protected, so acetylation of this is done. Now we can do the reduction of this. Now if we do the nitration again, then this NH2 group will direct the nitro group at this position. Okay. That is ortho to this position, ortho to the NH2 group, nitro group will come over here. Now we can remove this NH2 group. Now the T protection of this amino group can be done. So now we can remove this NH2 group via diazotization reaction. Okay, so first it would be converted into diazonium salt, and then in presence of this H3PO2, so then we will have a H over here. Okay, and it can further be reduced, this NO2 group can be reduced, and if we will have the target molecule. Okay, so like this we can have a two ortho-para directing group meta to two ortho-para directing groups meta to each other. So this is about the guidelines for the disconnection of aromatic target molecule. Okay, thank you.